Hello students, in this video of chapter number 3 matrices and determinants, we will learn how to solve system of linear equations for singular matrices, that is the matrices whose determinant is equal to 0. So as we have discussed case 1 already, that if the matrix A is non-singular, that is determinant is not equal to 0, this is the case of unique solution and we can use matrix method to solve that system of linear equations. Whereas in case 2, if the matrix is singular matrix, then we cannot use that method in which we use inverse as 1 upon determinant A into adjoint A, right? So in this method, we will calculate adjoint of A into B, right? So adjoint of A into B, the product of adjoint A matrix and the B matrix, that is the constant matrix. Now the two cases which arise are, if number 1, adjoint of A into B is not equal to 0. 0 means is not a null matrix or 0 matrix. Then solution does not exist, right? And the system of equations is said to be inconsistent. So we will compute adjoint A into B. If it turns out to be not equal to 0, then solution does not exist and we say that the system is inconsistent. Whereas in second case, if adjoint of A into B comes out to be 0, then system, it may either be consistent or it may be inconsistent according as either system have infinitely many solutions or no solutions. So let us discuss one by one. Now let us take question here. So question number 1 here I am going to take is, which of the following system is consistent? Okay, the question will be like, which of the following system is consistent, right? And if consistent, solve them. If consistent, solve them, right? So let us take one system. So it is your 3x minus y plus 2z equal to 3, 2x plus y plus 3z equal to 5, x minus 2y minus z is equal to 1, right? So let us take this system. Now we know that this system can be written as the product coefficient matrix 3 2 1 minus 1 1 minus 2 2 3 minus 1, and this as x y z, and this as 3 5 and 1, right? So that is, it is of the form Ax is equal to B, where who is A? The coefficient matrix is 3 2 1 minus 1 1 minus 2 and 2 3 minus 1. X here is the variable matrix and B is the constant matrix. So first of all I need to check the behavior of our determinant, minus 1 1 minus 2 2 3 minus 1, right? So let us check the determinant. It is minus 1 into plus 6 plus 1 into minus 2 minus 3 plus 2, and this is minus 4 minus 1. So it is 15 and it is minus 5 and it is minus 10. So it turns out to be 15 minus 15, that is 0. So determinant A here is 0. This thing implies A is singular. It is non-singular. It is not non-singular, right? So in case of non-singular, we can use our A inverse like A adjoint A upon determinant A. But here this method will not work. So I have to compute adjoint A into B, right? So let us frame adjoint matrix. Now my given matrix A here is 3 2 1 minus 1 1 minus 2, and it is 2 3 minus 1, right? So frame the adjoint C11 C12 C13. So let us carry out the negative sign here. It is your minus 1 plus 6, that is 5. Here it is minus 2 minus 3, that is 5, and here it is minus 4 minus 1, that is minus 5. So adjoint of A without transpose, right? I have to take the transpose here. So this is 5, 5 and minus 5. Okay, 5, 5 and minus 5. Now let us take 2, 1, 2, 2, 2, 3. So this will be with negative, this will be with negative. So it is 1 plus 4. So it is 1 plus 4, that is minus 5. For second one, it is minus 3, minus 2, that is minus 5. Okay. And for the third one, it is minus 6 plus 1, that turns out to be 5. So it becomes minus 5, minus 5 and 5. Now for 3, 1, 3, 2, 3, 3. This is minus. So for 3, 1, it is minus 3, minus 2, that is minus 5. For this, it is 9 minus 4. So it is minus 5. And for last one, it is 3 plus 2, that is 5. So it is minus 5, minus 5 and 5. So let us take its transpose to get the adjoint matrix. So this becomes 5, 5 minus 5, minus 5, minus 5, 5, and it is minus 5, minus 5 and 5, which is the required adjoint. Now let us compute our adjoint of A into B. So adjoint of A is 5, 5 minus 5, minus 5, minus 5, 5, and it is minus 5, minus 5 and 5. And B is my constant matrix, that is 3, 5, 1. So let us compute the inverse product. Okay, let us compute the product of this two matrices. Okay, so it is your 15 minus 25 minus 5. It is 15 minus 25 minus 5. It is again minus 15 plus 25 plus 5. Okay, so it turns out to be, this is say minus 15, this is also minus 15, and this is your 15. So you find that it is not a null matrix, right? So adjoint of A into B here is not equal to 0. So as per case number 1, the given system is inconsistent. Given system is inconsistent. What does it mean? It means that it has no solution, right? So if adjoint of A into B is not equal to 0, system is inconsistent, and we say it has no solution. So let us take other example, and that example is your, again check the consistency and inconsistency and hence find the solution. So system here is x minus y plus z equal to 3, 2x plus y minus z equal to 2, and x plus 2y minus 2z is equal to minus 1. So again, let us, given system can be expressed as Ax equal to B, where A is the coefficient matrix and it is x is 3 to minus 1, where this is your A, this is your x, and this is your B. Okay? So firstly I need to check my determinant. So it is 1 2 1 minus 1 1 2 1 minus 1 minus 2. So determinant here is minus 2 and it is plus 2, and this is plus 1 is minus 4 and plus 1 here it is 4 minus 1. So it is 0 minus 3 plus 3, which is 0. So determinant A here is 0. This thing implies A is your singular matrix. So that means inverse method will not work here. So I need to compute adjoint of A into B, and we will check what kind of result is going to give us. So for adjoint of A, I will again frame the cofactors, and my matrix A here is 1 2 1 minus 1 1, 2, and it is 1, minus 1, minus 2. Okay. So let us frame the cofactors. So C11, C12, C13. So here it is minus 2 plus 2, and it is plus 2. This is 0. For second it is minus 4 plus 1. It is 3. For third it is 4 minus 1, that is 3. So it is 0, 3, 3. For second it is 2, 1, 2, 2, 2, 3. So this is negative, this is negative. So this is 2 minus 2, that is again 0. For second it is minus 2 minus 1. Okay. So minus 2 minus 1 is minus 3. And for third it is 2 plus 1, that is 3. So it is 0, minus 3, minus 3. For third it is 3, 1, 3, 2, 3, 3. So this is negative. This is 1 minus 1, that is again 0. Second one is minus 1 minus 2, that is minus 3, right? Minus 1 minus 2. And for last it is 1 plus 2, that is 3. So this is 0, 3, 3, right? So adjoint will be like 0, 3, 3, 0, minus 3, and 0, 3, 3. Now let us compute adjoint of A into B. So adjoint of A into B, B was 3, 2, minus 1. So let us compute this product. So this is 0 plus 0 plus 0. Okay. Then it is 9 minus 6 minus 3. And third one is 9 minus 6 minus 3. So very clear that this turns out to be a null matrix. That means adjoint of A into B is equal to 0, right? Now the given system may be consistent. The system may be consistent, and if it is consistent, then it have infinitely many solutions. So it may have infinitely many solutions. Okay. So to find those solutions, how we will work out? We will consider to find solution. What we do? We will consider first two equations. Consider first two equations. So what are the first two equations? First two equations are like x minus y plus z equal to 3, and other one is 2x plus y minus z equal to 2. Right? So it will take this z to other side. Now I will reduce it to a 2 cross 2 system. Okay, and take y as constant now, and it will be taken to other side. Right? So this is number 1 and this is number 2. Right? So again one method is there that you again start with a 2 cross 2 system now. Again compute determinant A and go for adjoint A into B checking. Okay, or if this determinant A turns out to be your not equal to 0, means if it is the case of non-singular matrices, then you can apply matrix method and can get the answer. But instead of that, the very simple thing is, because I need just value of x, y and z, I can simply add them also. So this will be better. Add 1 and 2. So what do I get by adding? It will be your 5. Okay, so x turns out to be 5 by 3. Right? Now substitute it somewhere here. So x minus y equal to 3 minus z. So x here is 5 by 3. So I will put it in this equation number 3. This thing implies 5 by 3 minus y equal to 3 minus z. Okay. So 5 by, because that is, we are taking z as constant. So it will be 5 by 3. I am taking y to this side. Minus 3 plus z is equal to your y. So it is 5 minus 9 and plus 3z upon 3 equal to y. So implies y is equal to 3z minus 4 upon 3. Okay. Now let us take our z as k. So you can take z k here also, from here also you can take it, where what is k? K is some arbitrary real number. Okay, so as it is arbitrary real number, so it will give me x as 5 by 3. But my y here is your 3z minus 4 by 3, right? Which can I write, because I'm taking z as k, so I can write as 3k minus 4 by 3, or it can be written as k minus 4 by 3. Now, as k is your arbitrary real number, so keep on changing k, y will change accordingly, right? So x is only fixed here, so therefore this system will have infinitely many solutions. Okay, so the infinitely many solutions are given by x is equal to 5 by 3, okay, y is equal to k minus 4 by 3, and z is equal to k, where k is a real number. So this is the way how we solve the systems in which your matrices are singular.